Let's look at the trigonometric integral arctan x is equal to the integral of 1 upon 1 plus x squared dx. Now this is a very useful integral and we can use it in order to solve lots of other integration problems. Now what is it telling us? Well, we know that the function tan x goes from an angle to a length. So if you were to put in a value for x, which is an angle, then the tan of x would give us a length. Now the inverse function is called the arctan function. And in the inverse function, we go from a length to an angle. So in this instance here, the value x is a length, and when we find the arctan of x, we get out an angle. And this integral tells us that the angle that we get out is 1 upon 1 plus the length squared, all integrated. Now it's going to be much easier going forward if we differentiate both sides of this equation. So we're going to have d by dx arctan x, and on the right hand side we're differentiating the integral. So we're just going to be left with our 1 upon 1 plus x squared. So this here is an equivalence of this. We write it in this format because it's much easier to see the connection between the arctan and the 1 upon 1 plus x squared. So let's look at the arctan function. So we can see here the arctan function in pink. Now remember, along this axis we're going to have a length, and then up this axis here we're going to have an angle. So we're going from length to angle. Now what we want to do is differentiate this function arctan x. So you can see here, if you just look at it, that the gradient along this line here, well, it's pretty flat. The gradient in effect is close to a value of 0. So we should have a line that comes along at 0 here, but you can see here the gradient starts to increase until eventually you get to a point here, 0. Now at this point here, it looks like the gradient is approximately equal to 1. So that is, we'll go along 1 and up 1. So that means that we're going to have a graph that comes along like this, and it goes up to the point 1. And then the gradient is going to become less and less until eventually it goes to 0 again. So again, it's going to come along and down like this. So we're going to have a function that comes along, goes up to the point 1, and then comes back down. So we can actually see that if we were to put in the tangent line to the function arctan x, and this is the tangent line being added here. So let's move this tangent line along, and we can see that the tangent line is the actual gradient of the point in pink. And you can see the dotted line in blue above is the gradient of the line in pink, which is our arctan function. So you can see when we get to the point 0, we're going to have a line here which is gradient of 1. So the height of this is 1. And we can continue along, and you can see the gradient decreasing until eventually it goes to 0. So the function in pink is the arctan function. The function in blue dotted is the differentiation of this arctan function. So if this is correct, then whenever we differentiate this arctan function, we should just get the function 1 upon 1 plus x squared. So let's put this function 1 upon 1 plus x squared on the diagram. So you can see here that the function 1 upon 1 plus x squared here is exactly d by dx arctan x. So it means that whenever we differentiate arctan x, we get 1 upon 1 plus x squared. Therefore, if we were to integrate this side here, we get back to arctan x. And if we integrate this side, we must integrate this side, in which case we get 1 upon 1 plus x squared dx. So this shows us graphically that the arctan x is equal to the integral of 1 upon 1 plus x squared by dx. Now that's the end of this video. In the next video, I'm going to show you an actual geometric proof that this is actually true. So thank you for listening. I'll get you on the next video. Goodbye.